Okay, today's section is called Right Triangle Trigonometry. We're going to have you learn to evaluate trigonometric functions of acute angles and use fundamental trigonometric identities. We also want you to use a calculator to evaluate trigonometric functions and use those trigonometric functions to model and solve real-life problems. So we're getting to more complex stuff now with our trig functions. So let's first recall our 6 trig functions, SOHCAHTOA. Okay, that's the abbreviation for the first 3, which says that sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. And tangent of theta is equal to opposite over adjacent. Okay, and these are the building blocks of all the trig functions. Okay, we know cosecant is the reciprocal of sine, which means it is hypotenuse over opposite. Secant is the reciprocal of cosine, which makes it hypotenuse over adjacent. And cotangent is the reciprocal of tangent, which makes its equation adjacent over opposite. Now, by now we've given you a couple different ways to calculate sine, cosine, and tangent and the reciprocal functions. They're all built off of this whole concept that we have a right triangle, we have an angle theta, and we're trying to calculate a ratio between two sides, okay? The side opposite theta, or the side adjacent to theta, or the hypotenuse. Okay? So, last lesson we talked about sine of some angle being y, and cosine being x, and tangent being y divided by x, okay? So all of these are talking about the same thing, okay? In those cases, those functions were using this right triangle as being part of a coordinate plane, okay? So if we're talking about a coordinate plane and we've got some angle theta here, okay, and we've got a hypotenuse equal to 1 in our unit circle, then opposite would just be that y coordinate, right? Some y coordinate. Okay, so that's how we reconcile these two sets of functions. Okay, this second set is used for the unit circle. Okay, we're going to give you another set of functions that help you generalize this to any size triangle in the coordinate plane later on. Cosine, of course, is adjacent over hypotenuse, so that'll just be our x. And tangent is opposite over adjacent, so that would be y over x. Okay? So we flip those over and get their reciprocals for our reciprocal functions. Okay, and that's how we really look at the 6 trig functions. I wanted to kind of bring that together for you guys. So let's talk about trig functions of special angles. Again, we already calculated these in the last lesson. This is a nice, concise table for sine, cosine, and tangent of the 6 trig functions. We see this put into practice in our unit circle, okay? Now, the important thing with these numbers is that they can all be rotated into 3 other quadrants, okay? So say we have an angle that we're dealing with in another quadrant, but that angle has what we call a reference angle, okay? So say I'm dealing with the angle 135 degrees. That angle is going to have what we call a reference angle, or the rest of the way over to the x-axis is what we're really measuring, of 45 degrees, right? So I can use a 45, 45, 90 triangle to measure that 45 degrees, okay? And I can use these numbers for sine, cosine, and tangent, but recognizing that they are going to be in a different quadrant, their values will change a little bit, okay? So y is positive in the second quadrant, so my sine will be positive. X is negative in the second quadrant, so cosine would be negative. And because tangent divides the two, Positive divided by negative would still be a negative, so tangent would end up being negative, okay? We could do that with the third quadrant. We could do that with the fourth quadrant. And we start noticing some trends with this, okay? So let's talk about those trends here in a bit. What we're going to talk about first is some fundamental trig identities. Now, we've kind of alluded to these in the past. Sine and cosecant are reciprocal functions, so 1 over cosecant is equal to sine, and cosecant is equal to 1 over sine of that angle, okay? Likewise, cosine and secant are reciprocal functions, so we can use 1 over cosine to get secant and 1 over secant to get cosine. And also tangent of theta and cotangent of theta are reciprocal functions, so 1 over cotangent equals tangent, 1 over tangent equals cotangent. And then to actually calculate tangent, we can take sine theta divided by cosine theta. And then to calculate cotangent, we can just flip this one over and get cosine over sine. So we call these first set of identities reciprocal identities. And then we call these second set quotient identities. And it's not really important that you know their names so much as you understand them. You understand how fundamental they are to the definitions of sine, cosine, tangent, and also their reciprocal functions, okay? So we want you to see them as opportunities, okay? You might see something and think, wow, I could really use tangent in terms of cotangent, or you might say, wow, I could really use tangent in terms of sine and cosine, okay? So we have opportunities to define tangent in more than one way, which is handy when we go to solve problems later on in this chapter. The third set of identities that we want to talk about is the Pythagorean identities, okay? And the Pythagorean identities are called that way because they're really derived from the Pythagorean theorem, okay? And when we put these triangles into a coordinate plane and then apply the Pythagorean theorem to them, we come up with these three Pythagorean identities. One of the first is that sine squared of some angle plus cosine of some angle squared is equal to 1. And we're using some different notation here. What I want you to really realize is that sine squared of theta is just a notation, and what it means is that I'm taking sine of some number, some angle theta. I'm finding that value, and then I'm squaring it, okay? Now, I don't know how they developed this notation. Maybe some publishers were looking to save space in books, didn't want to set all the type for it, whatever. But when we see sine squared and then the theta, that means that I'm taking all of sine theta and I'm squaring that number. So you need to know this because this is what you need to put in your calculator, even though what you see is the other, okay? And that applies to cosine squared theta, tangent, secant, cotangent, cosecant, okay? So we can rearrange some of these Pythagorean identities, and in class I might show you some of the derivations. But 1 plus tangent squared theta is equal to secant squared theta. And then 1 plus cotangent squared theta is equal to cosecant squared theta. Now, sine squared plus cosine squared equals 1 is really easy to remember. 1 plus tangent squared theta equals secant squared theta. I don't know, that one's kind of weird to remember for me. Maybe you remember it as the word its. I for 1, T for tangent, S for secant, okay? And then remember that cotangent and cosecant being squared together, they go together, and they're the other C's besides cosine, so that might help you remember it or something like that, okay? So when we're applying trig identities, it's important to recognize which identity is going to apply, and that's going to just take some practice. We're going to substitute it in or use it where we can, and then simplify. Now, there's going to be several different ways we do this, and you'll see throughout the problems that we practice in class how that will go. But let's try right now with this first right triangle. We have a side length 2 and a side length 5, and we have this angle theta right here. And I want to find cotangent of theta and cosecant of theta, okay? Well, cotangent is pretty easy, right? We have opposite and adjacent, and we know that cotangent is really adjacent over opposite, right? So that's going to be 2/5, right? So cotangent of this theta equals 2/5. Yay. But now I need to find cosecant. And without resorting to the Pythagorean theorem, how else could I do that? Well, I have a relation with a trig identity that says 1 plus cotangent squared theta equals cosecant squared theta, okay? So 1 plus 2/5 squared will equal cosecant squared theta, okay? So that's 1 plus 4/25. And that 1 is really 25 over 25, right? So cosecant squared theta equals 29/25, right? So cosecant of theta will equal the square root of 29/25, which is just square root of 29 over 5. And you're saying, wow, that doesn't look a whole lot easier to me, but it's just another way of doing it, okay? And sometimes when you get into situations in particular triangles, something like this may be the only thing you can use, okay, not just the easiest thing that you can use. So we start off using it in situations where it's not required, so that when you get into situations where it is required, you'll think of it. Let's talk now about some applications involving right triangles. Some of you may have seen problems where you have angles of elevation or angles of depression. I want to kind of give you a little bit of insight into what we're talking about, okay? So when we're dealing with an angle of elevation, we're going to have some observer here, okay? And the observer will be right here. And then we're going to have a horizontal type of perspective. And they're looking up some angle theta to some object. Maybe it's an airplane in the sky, maybe it's, you know, some control tower, I don't know, lots of different situations that you might have to deal with that, okay? The same thing applies with angle of depression, okay? So say you're the one in the airplane, right? And you're in the sky, and you want to look down at the control tower, and it's on the ground, but you're flying straight horizontal this way. The angle of depression would be that angle down from horizontal, an imaginary horizontal line, down to whatever object it is you're looking at below you. Sometimes this is a boat floating on the ocean and a sonar down to some object on the bottom of the sea type problem. Things like that you might see. So this problem here, an airplane in the air has an angle of elevation of 23 degrees with respect to the control tower. I should have said depression on that. Okay, has an angle of depression of 23 degrees with respect to the control tower, located 2,500 feet away from the end of the runway. If the plane is directly over top the end of the runway, so here I'm drawing a runway, and here I have my airplane, and here I have my control tower. Here's my horizon from the airplane's perspective, and here is my 23 degrees of depression. We know it's 2,500 feet away. Okay, so we've got this type of triangle thing going on, okay? 2,500 feet can also be put here. How high in the air is the airplane, right? So I've given you an angle, and I've given you a distance, and I need to know another distance, right? So I've given you adjacent, and I need to know opposite, so I'm dealing with tangent, right? Because tangent of 23 degrees should equal opposite, which is my distance, x, over 2,500 feet. So x should equal 2,500 times the tangent of 23 degrees. So, of course, we'll get out a calculator for this to be able to figure out tangent. We'll type in 2,500 times tangent 23 And then always make sure for your document that if you're using degree settings, you have it set up to be in degrees, because it might not be. So 2,500 times tangent of 23 gives you 3,970 feet in the air. Okay, so that's how far the plane is over top the runway. That's pretty far up. So chances are that plane's not going to land there right now. So what we've learned to evaluate trigonometric functions of acute angles, okay, and that was our special angles that we learned with. And we've learned to use the fundamental trig identities. We've learned what they are. We've learned to use a calculator to evaluate trigonometric functions, and we've talked about how to use trig functions to model and solve real-life problems. So we're going to do more of this in class. You'll get a better idea of how we use these trig identities and how they start popping up in the most unexpected places throughout trig. That's it for now.